For this lesson, we are going to be doing another couple of curve sketches for two functions that are slightly more complex because they have asymptotes. And we talked in our limits section about a bit about discontinuity and also about horizontal asymptotes and how to find them. So now we're going to put that all together with what we've learned about derivatives in order to be able to complete a curve sketch of a couple of functions with asymptotes. Okay, so let's just recall where we will find our discontinuities. So we have certain kinds of discontinuities for rational functions. So we're going to be looking specifically at rational type functions and related. So maybe some rational functions, some functionals that involve a fraction but also have a radical in them. Okay, so anything with a fraction. Okay, so vertical asymptotes occur where the function is not defined, which is where the denominator equals 0. Okay, equals 0 and does not cancel with a term in the numerator. Okay, we have a point discontinuity or a hole if the discontinuity is removable, which means the 0 in denominator cancels with a 0 in numerator. So if they have the same 0 and you can cancel it out, you have a point discontinuity or a hole. If they don't cancel out, you have an essential discontinuity or a vertical asymptote. The other kind of discontinuity we've seen, a jump discontinuity, typically will occur when you have a piecewise function that doesn't match up. There aren't as many functions. There's some absolute value functions you can get with an absolute value divided by like a rational function with an absolute value in it, where sometimes you can get a natural jumping discontinuity, but usually it's to do with piecewise functions. So we have our discontinuities that we need to look for, and that's something that if we see a denominator, we are always going to be instantly looking for. The other thing we're going to have to look for is horizontal asymptotes, which are not discontinuities. You can cross a horizontal asymptote. That's something I often have to remind people. So horizontal asymptotes we looked at in our limits unit, where it's where the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x. So it's what's happening as x attains extreme values. Often a horizontal asymptote is when those are equal to a number, when they're not just infinite. If it's infinite, it says that the function just continues increasing. If it's negative infinity, it says the function just continues decreasing infinitely. It doesn't approach a particular number. Okay, so let's look at a couple of curve sketches and see how we integrate it. So these are going to be places, vertical and horizontal asymptotes are going to be part of our examination of the original function. So when we're looking for x-intercepts, when we're looking for y-intercepts, we're going to be looking also for our vertical and horizontal asymptotes. So example 1. Okay, we're going to say we want to sketch f of x equals x squared plus 3x minus 10 over x squared minus 4. Okay, so the very first thing we should do when we have this is look for discontinuities, because discontinuities we're not going to be able to even find x-intercepts until we know whether we have any terms in the numerator that are discontinuities. So when I see irrational functions, polynomials in the numerator and denominator, first thing I'm going to do is going to be to factor. Okay, so what we are going to do is we are going to look at our we are going to look for discontinuities. Okay, and this is discontinuities in f of x. So we have, and you'll notice often anything, so if you have a vertical asymptote in f of x, f prime of x also won't exist there, and neither will f double prime of x. A vertical asymptote is something that the derivative won't exist there. Same with a whole. The derivative doesn't exist there because it's not differentiable at that point. So let's look for discontinuities. So we're going to rewrite f of x. It's equal to, the top we can factor to x minus 2, x plus 5. And the denominator factors to x minus 2 times x plus 2. And we see here the x minus 2's can cancel. So we need to automatically, write down, we have a point discontinuity at, and so the x coordinate is going to be the 0 that we canceled. So we canceled the 0 that occurs at x equals 2. So x minus 2, that would have been 0 at x equals 2. So the x coordinate of our point discontinuity is going to be 2. It stops existing at 2 just for a moment. Okay. Now to find the y coordinate, what we're going to do is we're going to plug 2 in to what's left over to see where is it heading to. Because everywhere except 2, that term cancels out. Just at 2, it doesn't exist. So if we plug in 2, we can see the limit. Okay, so when we're finding a point discontinuity, we're looking for the limit as x approaches 2 of f of x. Okay, so the limit as x approaches 2 of f of x is 2 plus 5, which is 7, over 2 plus 2, which is 4. So that is not 7/2, it is 7/4. That is how we find the y coordinate of our point discontinuity. Okay, so now we still have a denominator of our fraction. We still have a 0 for our denominator. So -2 would make our denominator 0. So that means we have a vertical asymptote at x equals -2. Okay, so those are the two discontinuities that we are going to need to do that. And I'm just going to put a box around any important information that we are going to want to include in our final sketch. Okay, so I'm actually going to make it a big box around vertical asymptote at this point and point discontinuity at this point. We need those to be in our final sketch. Okay, so we've done our discontinuities. Now that we've done our discontinuities, we can look for x-intercepts. Just like we did in our final one. So our x-intercepts, we're going to find where the numerator is equal to 0 for a fraction. So the numerator is equal to 0 here, so we have x plus 5 equals 0, x equals -5. We plug that in, our numerator is 0. Our y value, when x equals -5, we get 0. So that's our x-intercept. So we have -5, 0 is our x-intercept. We're going to do our y-intercept. In this case, since we don't have a 0, 0, it will be different, unlike the last lesson. So y-intercept, I don't want an s, it's a function, there won't be more than one. So now we're just going to plug in x equals 0. So f of 0 is 5/2. So our y-intercept is 0, 5/2. And so that's another point we have to graph, okay, to tell what our graph is doing. Okay, so now the last thing we have to do with the original function is find whether there are any horizontal asymptotes. And so what we are going to do is horizontal asymptotes. Okay, so the horizontal asymptotes, we are going to take the limit as x approaches infinity. We can leave out the whole just to make things simpler. And we're going to look at x approaches plus and minus infinity together. There's no square roots, so there shouldn't be anything too different about that. So the limit as x approaches plus and minus infinity of x plus 5 over x plus 2. Okay, so this is the limit as x approaches plus and minus infinity of x over x plus 5 over x over x over x plus 2 over x. So this goes to 0, this goes to 0. So we end up with 1 over 1, which is 1. So that means we have a horizontal asymptote at y equals 1. Okay, that's another important piece of information. Put a box around it. Okay, so now we are going to want to go and we're going to want to look at our f prime and our f double prime. So let's see what we've done so far with example 1. We've got that part of our sketch. So now we are going to go over here and I'm going to actually use the space over on, if it will let me, which it won't. Let's see, will you let me? Will you let me? No, you won't. Okay, we'll just keep going down and then we'll try to sketch over to the side once we're done with that. Okay, so now we're going to look at what happens with f prime of x. So we're going to look for critical points. Okay, and any other information we can get. So f prime of x. Okay, so we have f of x equals x plus 2, x plus 5 over x plus 2. So low d high is x plus 2, okay, times 1, minus high, which is x plus 5, d low, which is 1, square the bottom, and there you go, x plus 2 squared. X plus 2 minus x plus 5 is just negative 3 over x plus 2, the quantity squared. So what we can notice here is the denominator. So first of all, if we have a numerator that's a number, we do not have any critical points. So 0 equals negative 3 times x plus 2 squared. This has no real solutions. There's no way we can get 0 with a non-zero numerator. In order for a fraction to be equal to 0, the numerator must be equal to 0. Negative 3 can't be equal to 0. Okay, so no value of x is going to yield 0. Okay, so this means no critical points. We do have something happening at x equals negative 2. So f prime of x dne at x equals negative 2. But if we look back, we already have a vertical asymptote here. So this is because of the vertical asymptote. So because the vertical asymptote we have, it doesn't exist, so we don't need to investigate that as a critical point. But we do need to always, when we're making our sort of design chart, we do need to put vertical asymptotes in because they can change, f of x can change from being decreasing to increasing, or it could potentially change concavity at that point. So we do need to investigate that. Okay, so the other thing we may want to notice here when we're going through and making our chart is that if the numerator is negative and we have something squared in the denominator, the numerator, our f prime of x is always going to be negative. Okay, so might just want to add a little note here that this is always negative. So this means f of x is always decreasing. Interesting. I wonder how that's going to look. Okay, so finally, we have our critical points in our f prime. Let's look at f double prime of x. Okay, so that means points of inflection. So critical points, this is f prime of x, and points of inflection is f double prime of x. Okay, so we are going to go to our derivative and we're going to say low d high is nothing minus high times d low. Using the chain rule, we have 2 times x plus 2, so 2x plus 4, so negative 3 times high d low, so times 2x plus 4, so it's a minus minus, so it's 6 times x plus 4, sorry, 6 times x plus 2. Square the bottom and there you go. So f double prime of x equals, so negative 3 times 2 is 6 times x plus 2 using the chain rule, and square the bottom, we have x plus 2 to the 4th power. We're going to cancel that, and that leaves us with x cubed. Okay, so it's 6 over x plus 2 cubed. Okay, so here we notice again that this is never 0. So this means, so 0 equals 6 over x plus 2 cubed has no solutions. So that means that we are not going to have any points of inflection. But we do have a place where the second derivative doesn't exist, which is again x equals minus 2. And we might notice that we're going to change sign there. Okay? So let's go ahead and draw our chart and then draw our sketch. And I'm going to try to see if we can't zoom out so we can kind of see everything from example 1. So it's a little bit small, but hopefully you're able to see that. So we can put this into first a little sketch chart and then a real sketch. Okay, so our points where things are changing are supposed to be our critical points, points of inflections. We also need to include vertical asymptotes in this sketch. So negative 2 is a vertical asymptote. So you can put a little star next to vertical asymptotes because those are going to have to go in our little, because derivatives you can change from being increasing to decreasing at a vertical asymptote. You can also change concavity at a vertical asymptote. So we need to look at the signs of f prime and f double prime at those points. Okay, we don't have any critical points, so we don't need to put any of those in. And we don't have any points of inflection, so we don't need to put those in. So really, we're just looking at what happens to f prime of x on either side of negative 2 and what happens to f double prime of x on both sides of negative 2. Okay, so f prime of x, when we're smaller than negative 2, we're negative because the bottom is squared, so it'll be positive. And when we're bigger than negative 2, we're still going to be negative because negative divided by a positive. And no matter what number we plug in for x, it's always going to be f prime of x is always going to be a negative divided by a positive. F double prime of x, when we are below negative 2, the denominator is negative and the numerator is positive, and a positive divided by a negative is negative. So here, on the other side of negative 2, we get bigger than 2, so it's a positive divided by a positive, which is positive. So we are decreasing and concave down. So in this region, so this is not a 0, this is a D and E, does not exist. So we're going to look like that. And here we are decreasing but concave up, so we're going to look like that. And if we think about where our points are, that actually is starting to look a bit like something we're familiar with, which is kind of like a hyperbola with a vertical asymptote. So let's now take this to draw an accurate sketch. Okay? So we're going to first start by looking at our points. So we have negative 5, 0, 0, 5 halves, 7 fourths. We're probably going to be okay with just doing like a 1, 2, 3, 4, 5, and negative 1, negative 2, negative 3, negative 4, negative 5, and then a 1, 2, 3, 4, 5, and then negative 1, negative 2, negative 3, negative 4, Probably didn't have to write all those numbers in, but we're just going to assume we're counting by ones. In fact, I'm probably going to erase them. If you just put numbers in, unless you write them in, I'm going to probably assume you are counting by ones. If you want to use a different scale, please write them in. But for now, I'm just going to use that so that you can see more clearly what points we're drawing in. Okay, so we are now going to do, first thing, just like when we're doing rational expressions in Pre-Cal 12, the first thing you want to do is your asymptotes. So we're going to do a vertical asymptote at x equals -2. And we have our x-intercept at x equals 1, 2, 3, 4, x equals -5. We have our horizontal asymptote at y equals 1. We're going to put a dotted line in there. And I'm going to put in any of the other points. I have a y-intercept at 0, 5 halves, which is 2.5, so that's going to be right here. And I also have a hole at 2, 7/4, which is just under 2. So it's going to be right about there. Okay, so notice with the point discontinuity, I am literally going to draw it like a hole that is around that x and y value, and then we are just going to connect our dot through there. Okay, so now we know that the down part is going like this. So it's going to curve down like that towards our vertical asymptote. So we're concave down and we are decreasing. So the top, we are continuing to decrease, but we're actually going to start from up here so we can get that lovely concave up shape. We're going to go through the points we need to go through, and then we're going to head out to our horizontal asymptote as well. And we are going to write in, we've got y equals 1, we've got x equals -2, we've got 2, 7/4, we have 0, 5 halves, and we have -5, 0. And those are the key points that we want to make sure that we get into our graph so we know that those are accurate. Okay, so let's look at one more curve sketch here. Let's just take one more gaze at the beauty of this lovely, lovely curve sketch. Okay, so it was a lot of steps just to get this simple thing, but it's really important to know that you're sort of checking all things because functions can sometimes surprise you. So this lets you see exactly what's happening at every stage. So let's look at a second example. Okay, and in some ways this example is simpler. So let's make this the nice. Okay. So example 2. Okay. We have f of x equals 4 over x squared plus 2 plus 1. Okay. So we're going to check first for discontinuity. And actually, there's none, even though we have a rational function, because x squared plus 1 is never equal to 0. Because x squared is always positive. You can't add a positive to a positive and get 0. So there are no discontinuities in this function, and that's going to be pretty helpful. Okay. Do we have a horizontal asymptote? So we can see if we can find, let's actually look for an x-intercept. Okay. Well, we have a number in the numerator and no variable, so there are no x-intercepts. And the y-intercept, when we plug in y equals 0, y-intercept is 0, 4. And plug in 0, we get 4 over 1. Okay, horizontal asymptote, and I'll actually write that out. Okay, we have, I'm going to take the limit as x approaches plus or minus infinity, shouldn't matter, we have an x squared of 4 over x squared plus 1. This is the limit as x approaches plus or minus infinity of 4 over x squared over x squared over x squared plus 1 over x squared. This is all going to go to 0. So 0 over 1 is going to give us 0. So we have a horizontal asymptote of y equals 0. So thus far, the only really important piece of information we have is there's a y-intercept and there's a horizontal asymptote. So what does this thing look like? And this is going to actually, this is one where we actually do want to take the derivative. So the derivative and the second derivative here are actually going to give us most of our information, because other than that there's a y-intercept and a horizontal asymptote, I know nothing about this function. So let's look at critical points and f prime of x and see what that can tell us. Okay, so we're taking the derivative of a rational function. Low d high is 0 minus high times d low, so minus 4 times 2x, so that's minus 8x for our numerator. So f prime of x, and if you need to write out the quotient rule, you go for it. Okay, I'm just doing this to save you guys some time because I'm hoping you're pretty good with the quotient rule by now. Square the bottom, and there you go. So we have minus 8x and x squared plus 1 in brackets squared. Okay, so where is this the denominator? There are no discontinuities. F prime of x exists everywhere. So when we have 0 is negative 8x, we get x equals 0. So we have a critical point at x equals 0. Okay? And if we look back, that was our y-intercept. So we have a critical point at 0, 4. Okay, and we're going to throw that into our chart. And so now let's look at f prime. So we'll think about where it's increasing and where it's decreasing. So points of inflection, f double prime of x. Okay, this is somewhat more fun. So we're going to do low d high. So negative 8 times 8x squared, so f double prime of x is low d high, so negative 8 times x squared plus 1 squared, minus high, so plus 8x times d low times 2x squared plus 1 times 2x. Square the bottom, and there you go. So we get x squared plus 1 to the 4th. Notice we have a factor of x squared plus 1 we can factor out. So let's simplify that. We can even factor out an 8. So let's factor out an 8. Okay, so we have an x squared, so we can cancel there, make that cubed. So we have an 8, and then that is, we are left with a negative 1. We'll put that at the end, minus 1. So in the front, we've taken out an 8, so we have 2 times x times x. So we have 4x squared minus 1. Okay, so 8 times 4x squared minus 1. That 1 is the only thing that we're left with when we factor out the 8 from the front. And then that's over x squared plus 1. Okay, so we're going to want to calculate cubed. So x squared plus 1 cubed, we still don't have any points where this doesn't exist, so that's awesome. So our points of inflection is where 0 is equal to 8 times 4x squared minus 1. Can divide by the 8, add 1 to both sides, so we get 1/4 is x squared, and x equals plus and minus 1/2. Okay, so we are looking for what our y values are at that point. So in order to find, these are our lovely points of inflection, we actually have to go back to plus minus. We've got this plus minus 1/2. We have to go back to our original function of 4 over x squared plus 1. So this is 4 over 1/2 squared plus 1, so 4 over 5/4, which is 16/5. So we have positive 1/2 16/5. Okay, and it might just be easier to divide this. So 16/5 is 32/10, which is 3.2. So 1/2 3.2, because we're going to be graphing this. So this might be a little easier to do that way. So 0.5 3.2. And then negative 0.5, when we plug that in, we get 3/4, which is 16 over, we get negative 1/2 squared. It's going to be actually the exact same point because we're squaring it as we pointed out. So this is also 3.2. Okay. So now when we go back, what we are going to do is we're going to look at everything. These are important. These are our points of inflection. Okay. So let's make our chart and then we will try to graph this. Okay, let's see. We got everything in our view. Oops, we don't need that. So now what we're going to do is we are going to do our little chart. We have a few important points to look at. So we have our critical point at 0.4. We have our, and we're going to spread these out just so we can see what's happening. So we have our negative 0.5 and we have our 0.5. Okay, we're going to look at f prime of x and f double prime of x and do a sketch. Okay, so f prime of x, when we're smaller than negative 1/2, let's look at perhaps negative 1. F prime of x, if we have a negative 1, is going to be a positive numerator, so it's going to be positive. Okay, so it's increasing. When we switch to being between negative 0.5 and 0, we're still going to have a positive number in the numerator, so we will remain positive. When we cross 0, we're going to start to have a negative number in the numerator. F prime, when we're f double prime, when we're left with 0.5, so our numerator is always going to be positive because we're always doing 4 times a positive minus 1. No, it's not always going to be positive. When we are less than 0.5, we're squaring a number that's bigger, so 4 times that number is going to be bigger, so we are going to stay positive. The denominator will always be positive. Okay. When we cross 0.5, so we have something like less than 1/2, so take 1/4. If we square 1/4, we get 1/16. So we're going to have a negative numerator for our f double prime. On the other side of 0, we're also going to have a negative numerator when we get bigger than 1/2, so try x equals 1. 4 minus 1 becomes positive again. Okay, so that is positive. And now we're going to do our sketch. Okay, so this is 0 here, and these are 0 here. So these are our points of inflection. So concave up and increasing looks like that. We have a point of inflection here. Concave, we have still increasing, but now concave down is going to look like that. Decreasing and concave down looks like that. And increasing, we have another point of inflection here. This is a local max now, we know. And we are decreasing and concave up, which is going to look like that. So when I go to draw my sketch, I'm again going to start by putting in the actual points I know, which are 0.4. I'll put in a point 0.4. And I know that I have a horizontal asymptote at y equals 0. Okay. I also know that I have a point that is 1/2, so let's make this, we make this our 1 here. I know that I have a point that is 1/2 3.2, so it's going to be somewhere right around here, and negative 1/2 3.2, so it's going to be like that. That's going to be my point of inflection. So between here and here, my points of inflection, there's my local max, and then at that point of inflection, I am going to flip to being concave down. So, and then I'm going to head out for my horizontal asymptote. Okay, so those are the important points. We have 0.5, negative 0.5, 3.2, 0.5, 3.2, and those are actually accurate numbers as well, and 0.4. And those are the important points that we need to get in there. And we have to sketch our concavity properly, and that gives us a beautiful beautiful curve sketch, including discontinuities, asymptotes, and pretty much everything.